Hi, welcome to Dr. Raz, the Baking Chemist. So today's question, as promised last week, is a multiple choice entropy question. It's a year 2 question. And I'll show you 2 ways of how to solve it. One visual and one mathematical. In multiple choice questions, you really can't spend too much time on thinking of the answer. So I'm hoping it'll help. Okay, let's see. So the question is quite simple. As I said. It's which one of the equations below represents a reaction that is feasible at all temperatures, right? And they've obviously given you 4 options, as usual. So this is, obviously that reaction doesn't matter about the reagents, but you do need to look at the state symbols. So that reaction and the enthalpy change, that reaction and the enthalpy change, etc., etc. Okay, and so how do you deal with this question? Right. So let me give you the visual method, the easy method first. You need to remember this table, right? So the table goes something like this. So you write delta S positive, delta S negative, so entropy, positive entropy, negative entropy, and you write enthalpy negative and enthalpy positive. Okay, and then the way I remember is all, low, high, no. All, low, high, no. What does that actually mean? So all temperatures, low temperatures, high temperatures, and no temperatures. What that means is this. If a reaction has a positive entropy and a negative enthalpy, in other words exothermic, then that's feasible at all temperatures. If a reaction has a negative entropy and a negative enthalpy, then it's only feasible at low temperatures. And if a reaction has a positive entropy and a positive enthalpy, in other words endothermic, it's only feasible at high temperatures. And if a reaction has a negative entropy and a positive enthalpy, then it's not feasible at any temperatures. All, low, high, no. However, get these right. Delta S positive, delta S negative, delta H negative, delta H positive, and then all, low, high, no. Now, if other people, and I sincerely, this is a request, if other people know how to easily remember it, if you know a mnemonic, for example, if you know sort of a phrase to be able to remember this, I'm sure all the students will appreciate it. Okay, so please let me know in the comments below. All right. This obviously follows on from another entropy question that I did last week, so you can find that over here. But this question can be done by itself. All right. Multiple choice questions are notoriously sort of not difficult, but finding ways of quickly answering a multiple choice question. Remember, you're only going to have just over a minute per question. So we can all do with ideas, techniques, strategies, how to quickly answer questions. So I really mean it. If you know of any strategies how to answer multiple choice questions, all right, quickly, let me know. Okay, so moving on. So that's the visual method. All right. Now, obviously that means that you need to memorize this table, but knowing this, very quickly you can answer this question. So following that method, so I know it says all temperatures, so that means all temperatures. So that means the entropy has to be positive and the enthalpy has to be negative, in other words exothermic. So first thing is I'm only looking at exothermic reactions. So obviously that's out. That's out because that's endothermic. And remember, I'm only looking at exothermic. So the only 2 options are these and these. All right, so now you think, okay, well, I need the entropy to be positive. Okay, so both are exothermic, but entropy to be positive. So now here you're thinking, all right, so they're going from gases, state symbols now, isn't it? Gases to gases. So, okay, in terms of the phase, the state, it doesn't change. What about the number of molecules? So the number of molecules, there are 3 particles, so 2 of these and 1 of M's, so 3 particles going to 2. So the entropy is actually negative. Okay, I don't want a negative entropy, I need a positive entropy. Alright, so that is out. Okay, and what about this one? Well, I wouldn't even think about this one, I just say fill in the C answer and move on to the next question. But however, let's just see. So entropy is positive, so it's going from 1 molecule to 2 molecules. All right, and it's both gases. So gases doesn't really matter, but the molecules do. So it's going from 1 particle to 2 particles, and therefore that's the answer. So the answer is C. Okay, so that's a very quick, way of doing this kind of question. However, be aware, even if you think, all right, that's all I need to know, I'm always going to answer multiple choice questions based on that. Be careful, because this kind of a question can actually come as a structured question. In fact, they could give you this question. They could say, show why this reaction is feasible at all temperatures. Okay, so that could be a structured question. So be aware that yes, that will get you through most of the questions, and that's a quick way of remembering, what kind of temperatures reactions happen at. However, be aware that you may need a bit more thinking, a mathematical way, which I'm about to go through now. Okay, so visual, right? Mathematical way now, right? Mathematical way, and I'm going to start is this formula, Gibbs Free Energy formula, and please just learn it. Minus T delta S. Now let's say that this question was rephrased. So this wasn't a multiple choice question. This question was as a structured question. Yeah, they said, here's a reaction. Yeah, show why this reaction is feasible at all temperatures. All right. Now, I'll show you that particular question in a minute. Okay, but let's just show you. So what is this mathematical way? Well, look, we know in order for a reaction to be feasible, the delta G has to be 0 or less. So 0 or negative, yeah? So that means I need this to be 0 or less. Now, when am I going to get that delta G to be 0 or less? Well, if the enthalpy change is actually, let's say the enthalpy change is positive. It's a positive number, yeah? 10, 20, 100, 1,000. So a positive number. Okay? And the entropy change, now temperature is what I'm trying to find out, so I'm going to put temperature at the end, okay? But the entropy change, let's say, is negative, right? So that means that entropy is negative, so I'm going to say negative. In fact, let's just put negative like that. Okay, so what I've got, that negative is that negative in the formula, and that negative is the actual value entropy. Now think about it, if I have a positive enthalpy, and that minus and minus makes positive, so I'm always going to be adding a positive number to a positive entropy. Yeah. Now I'm going to use 2 separate examples of temperature just very quickly to see what happens. Yeah. Temperature of 0. Remember, temperature in this equation is always kelvins, right? Temperature equals 0, and temperature equals, I don't know, 1,000. Just a high number, a high temperature. Okay. What's going to happen? So if I now, so positive and positive is always going to be positive. The lowest temperature I can get is 0 Kelvin. So that means this expression will become 0, and so I will still end up with a positive delta G. And of course I know that won't be feasible because positive delta G. Yeah, it needs to be 0 or negative. So that means if I have a positive enthalpy and a negative entropy, I will never have this reaction which is feasible. This reaction will never be feasible at any temperature. Okay, and of course, going back to my table, just you might be able to see it just there. Positive enthalpy and negative entropy. Yeah, there's no temperatures where this reaction is feasible, and we found out mathematically. Yeah, let's use another example now. So I know that if it's a positive enthalpy and negative entropy, no temperatures is feasible at. Let's use a different example now, right? So that's one example. Let's now think, okay, let's say that this is a positive, so I've got a positive number of enthalpy, so positive enthalpy, all right? And remember, positive means, for enthalpy's sake, positive means endothermic, yeah? So positive enthalpy, and then minus for the formula, and let's say this is a positive entropy now, all right? So I have a positive entropy. Plus and minus is minus, isn't it, yeah? And of course a T, sorry. Plus and minus is minus, isn't it, yeah? So that means I'm going to have a positive number, take away a value, yeah, of delta S, and multiply by T. Yeah, so I'm going to take away a number from a positive value. Now, I think common sense, I hope you can see this, that if I take away a large, so let's say temperature is really 0. Let's just use 0. Let's use these two examples again. So temperature is 0. Now, if the temperature is 0, that means this whole expression becomes 0. And of course, I'm left with a positive delta G. Not feasible. So at low temperatures, 0 is not feasible. Right? So I'm going to write that down here as I'm doing this. So this is the second example I'm using. So low temperatures, it's not feasible. Okay? What about high temperatures? So if I have 1,000 here, right? So 1,000 here means this, so I'm going to have a positive number, take away a large number. That means I can get a negative number. So let's say this is 10, and this is 1,000. 10 minus 1,000 is, yeah, minus 990. So I can get a negative number. So if this is, large, so this expression is large, yeah, this expression is small, I can get a negative number. So in other words, at high temperatures, this expression will be big enough to make this entire thing negative. So positive minus a big number is going to be negative. So that means at high temperatures, yeah, this will be feasible. Low temperatures, no. High temperatures, yes. Perhaps I should put that down. Yes. Yeah, and sure enough, if you look at that, if you look at this table, positive entropy and positive enthalpy is high temperatures. It's feasible. Yeah. So remember, I made the mistake writing that down. Yeah. So this was supposed to be a positive entropy. Okay. But it's just that when this positive, yeah, is combined with that negative, plus and minus makes a minus. That's what it is. Okay. So again, using the expression, using that equation, you figured out whether a reaction is feasible, at what temperatures a reaction becomes feasible. Okay, and then of course the third one, yeah, is let's start using now negative enthalpy and minus for the formula, and let's use a negative entropy, and of course temperature. So now that minus and minus is negative. In fact, let me write that down. So delta H this time, my third example is delta H negative and delta S negative. Okay, and now let's see, is there any temperatures that I can get this reaction to be feasible? Well, that's a minus, that's a negative, and that minus and minus is plus, right? So I'm going to have a negative enthalpy, but then I'm going to add. Now, if this expression is large, that means negative number plus a very large number can be positive. Yeah, so if this is T is 0, so large, T is 0, so let's do the 0 like normal. So if T is 0, there's your 0. Okay, that means this expression becomes 0, so you end up with a negative delta G. So that means if at low temperatures, it is feasible. Yeah, but what happens at high temperatures? So that means high temperatures. If this is 1,000, for example, there's my my example. 1,000. That means I'm going to have this as a large number. This expression will become very large. So that means a negative number plus a very large number. I can actually have a positive delta G, and therefore at high temperatures, it's not feasible. Yeah. Remember, it doesn't have to be 1,000. It could be 1,000,000. Yeah. The point is that large numbers, at the large temperatures, yeah, the reaction becomes not feasible. Okay. Now, and the final example is if I have minus, so negative enthalpy, minus for the formula, and a positive entropy. Again, let's use the example. T equals 0. 0, that means that expression becomes 0, and that means I'm left with a negative. So therefore, so my final example is delta H is negative, and delta S is positive. And so what happens at 0, low temperatures? Low temperatures, I'm left with a negative enthalpy, and therefore it will be feasible. Yes, it will be at low temperatures. It will be feasible. Yeah, and then at high temperatures, so now I've got 1,000. So remember, this is 1,000. That means I'm going to get plus and minus is a minus. So 1,000, yeah, expression becomes very large. But remember, negative number, take away a large number, 1,000 times that, it's still going to be negative. So even at high temperatures, it's going to be feasible. So you can work this out through, through this equation. Yeah, you can logically think your way through. Yeah, and remember, in effect, when we do logically think through, what we're actually getting at is that table. Yeah, the one thing I am going to say is, don't ever leave multiple choice questions blank. It's my pet hate. When I see a student leaving a multiple choice question blank, it just annoys me no end. And the reason for that is this: you have 1 in 4 chance of getting it right. Let's say, you didn't know the answer at all. Well, just select one. Yeah, I mean, obviously you should know the answer. You should have done enough revision. However, if you don't know the answer, select one. Don't leave it blank. If you leave it blank, there's absolutely no chance you're going to get the mark. If you select completely at random, you've got 25% chance of getting it right. Okay, and if you're running out of time, so let's say you left it blank because you want to come back to it. Well, look, even when they say, right, you got 30 seconds left, or right, put your pens down. If you've done what I said to you, I mean, I tell all my students, if you ever leave a question blank, the first thing you should be doing is right at the top, yeah, of that page, just put a star. Yeah, because then when let's say you're short of time, you're quickly flicking through. What you're looking at is the star at the top because you left a question blank at the top. Yeah, or you want to look at that question again. So quickly flick through to the starred page, and then immediately, let's say they've said it, yeah, put your pens down, just select it. How about just fill it in? Done. Yeah, don't ever leave a multiple choice question blank. Don't ever, have I said this enough? Don't ever leave multiple choice question blank. Yeah, always fill in an answer. Now, let's answer this question, assuming it was a structured question. So assuming they said, oh, here's a question, show that this reaction occurs at all temperatures. So what you'll do is literally you'll do this. So you'll say, okay, well, delta G equals, and you always put this equation down, you know that, yeah? You get marks for it. T delta S. Okay, and so what you do is you say, okay, well, exothermic, so since enthalpy change is negative, it's exothermic, and literally you can say negative. And you can do this actually, negative minus for the formula, and then so the entropy is positive, y, put it down, positive, since 1 particle to 2 particles, or moles, or whatever you say, yeah, whatever you want to say. So delta is positive, and I'm putting that down in the actual exam question, right? So delta is positive since 1 particle is going to 2 particles. So that is positive delta S. Okay, delta H is equal to negative. Even though they've given you in that question there, exothermic, I'm putting the word in terms of symbols, it's negative. Yeah, and therefore I'm going to use that, and then I'm going to say delta G equals delta H minus T delta S, and then I'm going to say negative minus T, and then what is that? Positive, isn't it? Yeah, positive. Yeah, a negative number, take away any expression will always give you a negative number. So you'd probably put down, so a negative number, take away or minus any number will be negative. Therefore, delta G always 0 or below. Therefore, always feasible. Yeah, so you could actually show it that way. Yeah, but the point is, in a structured question, you'd have to put these expressions down. Yeah, annotate your sort of calculations. Yeah, delta S is positive. Why? Because you've seen that it's going from 1 particle to 2 particles, or 1 moles to 2 moles. Yeah, they're both sort of gases, so you can put that, I suppose, down. Depends on the number of marks. Yeah. So you can say it's both gases, so that doesn't really affect the entropy. But however, in terms of number of moles, it's increasing, so entropy is positive. Enthalpy is negative. Yes, I know, as I said before, they're giving you that it's exothermic, but you got to put it in terms of numbers. It's a negative, yeah, enthalpy, and therefore put that down, put that expression down, and therefore you've got to write something like this at the end. So negative number, take away any number will be negative. Therefore, delta G is always positive, always 0 or below. Therefore, it's always feasible. Yeah. So, I mean, yeah, I wouldn't be surprised if you do get more of these kind of questions, yeah, because these are quick questions where they can actually assess you on your Gibbs free energy knowledge very quickly, yeah, and whether you understand this equation or not. Okay, well, as I say, I promised I was going to do that, so there it is. If anyone does know of a better way, yeah, of doing this question or memorizing, this with a mnemonic or something, please let me know. I'm always looking for a mnemonic. When I was teaching GCSE in my previous college, one of my students came up with a mnemonic to remember electromagnetic spectrum. Radical monkeys in Wales uncover extra gold. Yeah, Richard of York gave battle in vain. You know about the white light, but this one I've been using ever since, and students love it because it's different. Yeah, so if you do know of a mnemonic to remember this, please let me know in the comments below. Okay. Any questions, any sort of suggestions, please let me know. My other, as I say, entropy videos, watch them. I've got a couple of them going through different questions, structured questions. And if you have any suggestions about what kind of questions I should go through, please let me know. Okay, and I'll see you next Wednesday. Bye.